Hello. Hello. It's okay.
Yes, sir.
Mm. So I think I'm audible here. Yes. So in the chat box, you can type your roll number just for sake of recording your attendance. Okay. So how do I maximize this? Yeah, now it's okay. So tonight we will continue this differential equation solution. We have already studied Taylor series method, where we have used Taylor series expansion of the function to find the solution at any point we desire once we know the initial value condition. So here also, this is another approach. Let's say we have a differential equation of this form, something like this. So it's a first order differential equation, fxy, it could be any function. And let's say this is the initial value condition. So that means at x naught, your y value is y naught. So x naught and y naught are the two initial the two initial values, like this y value at x naught, the initial values. So the Euler approach is a very simple approach in the sense that it takes what is called equation of a straight line uh, as a technique for finding a solution. Let's say similar to this, something like this. Let's say we have initial point here. So if you look at this graph here, let's say this is our initial point, and our initial point is, let's say, your x naught is here, and your corresponding y naught is here. So this is what is known to us, and uh, uh, we simply have this differential equation, and from what we are intending to find out is from this differential equation, by solving this differential equation, we are intending to find the functional form of y in terms of x. So once we know the functional form of y in terms of x, then we can predict the value of y at any value of x. So like in a Taylor series method, if you have your notes with you, we simply, in the Taylor series method, we see from this differential equation, we simply obtain the expression of y in terms of x. So once we obtain expression of y in terms of x, we put the value of x and then we find the corresponding y value. So that is what we did in Taylor series method. So solution of a differential equation, whenever we solve a differential equation, we try to obtain the functional form of y, independent variable, in terms of the dependent variable x. Once we know that expression, we can know the value of y at any value of x. So this is what the approach in Taylor series method. What we are going to do here is that, uh, of course, we don't know yet what is y in terms of x. The functional value form of y in terms of x is not known to us. We simply have a first order differential equation involving y and x. So let's say we have certain this thing, arbitrary functional form. Let's say the functional form may be something like this curve. And in this Euler approach, what we do is that we simply draw a tangent at this point. So by drawing a tangent at this point, we can consider a tangent. By drawing a tangent at this point, we have something like a straight line, something like this. And once we have a tangent, we simply find the slope of this tangent. How do we find the slope of this tangent? The slope of this tangent can be obtained by considering 2 points here. Let's say we consider another 1 point here. So let's say this point is your x, y point. We have our initial point x naught, y naught. Once we have a straight line, a tangent line like this, we can find the slope of this by writing like this. Slope is, let's say the slope m is y. This is our y, this is our x. So it will be y minus y naught, x minus x naught. This will give me the slope, right? So once we have this equation, this expression, we can write it like y minus y naught m into x minus x naught. Now m is the slope, and you also know that differentiation of a function at a point, differentiation of the function at a point, dy upon dx is simply the slope, that is del y upon del x when del x tends to 0. So if we take x minus x naught, that is del x, x minus x naught. If you take x minus x naught to be very small, if you take x minus x naught to be very small, then your slope, this ratio m will be equivalent to dy upon dx. So m will be equivalent to dy upon dx when you consider this increment del x to be very small. So del x is this is your del x. When you consider del x to be very small, your slope m will be equivalent to your differentiation dy upon dx. So once you have this condition, instead of dy upon dx, you can write the slope. So from this differential equation, first order differential equation, you can see that y minus y equal to y naught plus, instead of m, we can write dy upon dx, or you can also write x minus x naught f of x y. Okay, so f of x y, since we are calculating the tangent, we are calculating tangent at x naught y naught point. We are calculating tangent at x naught y naught point. So if you're calculating tangent at x naught y naught point, this tangent, the slope of this tangent, okay, the slope of this tangent over here, what you calculate here is the slope of this tangent. The slope of this tangent will be differentiation of y at x naught, isn't it? So instead of writing fxy, you should write fx naught y naught here. So this is our Euler equation. What we have here is this equation is called our Euler equation. This is called our Euler equation. So this is going to be like the expression of y in terms of x, the expression of y in terms of x by this Euler approach. Like in your Taylor series approach, you write a Taylor series expansion of the function y in terms of x. But in this Euler method for finding the differential equation, what we do is that we consider the initial point x naught y naught point over here, and we do not know the functional form of y in terms of x yet. We do not know. So let's say we have some arbitrary functional form, something like this. The only known parameters are this differential equation and this initial condition. So at this initial point, because we know this initial point x naught y naught, at this initial point we simply draw a tangent to this arbitrary curve which we do not know. So let's say the tangent is something like this, a straight line. So we can find the slope of this tangent. Once we find the slope of this tangent, the slope of this tangent will be differentiation of y at x naught. So because we are finding the tangent at x naught, so the differentiation of y at x naught, it will be your f, according to this differentiation, according to this differential equation, dy upon dx equal to fxy. So this will be f of x naught y naught. So this gives me my Euler equation. This Euler equation will be used to find the solution. So this is what we have discussed, and this I mean we can find like multiple points Like for example, if you want to arrive at this point, what we are going to do is that first we will obtain this point, your x1. Let's say this is your x1, y1, and at this point we draw a tangent again. Let's say the tangent is something like this, then we obtain this point, and we draw a tangent like this, we obtain this point, we obtain this point, we obtain this point. So like that, at any value of x, we are able to predict, we are able to calculate the value of y using this formula. So the formula is repetitive, something like this. If your initial point is x naught y naught, and if you are arriving at another point x1 y1, so this will be the relation, and x1 minus x naught is simply your increment h. And if you are going to arrive at x2, this is the formula you're going to use. So finally, the Euler formula is this. The Euler formula is this. So yn will be yn minus 1 plus h of f into this. So let us use the Euler method to find a solution for this. Here, what we are going to write here is, here what we have here is our first order differential equation, and from here you'll see that our fxy is, from the general expression, fxy is x cube plus y, and our x naught is 0, our y naught is 1, and our increment is x minus x naught. It will be 0.02. So like I said, your Euler equation, the general Euler equation will be yn minus 1 plus h f of x n minus 1 yn minus 1. This is the formula we are going to use. Okay, this is the formula. I hope you can arrive at this formula once you agree with this relation, because here simply we find a tangent at x naught y naught, and the slope m is actually your differentiation at x naught. So differentiation at x naught will be f of x naught y naught, f of x naught y naught, and we can arrive at the next point, y2, by using this. You can arrive at the next point, y3. Y3 will be your y2 plus h of f of x2 y2. So like that, the final formula you will arrive at this. Euler formula is this one. So now the approach is again quite simple. What is given to us is 0.02. Now we have to find, what is that? We have to compute the value of y at x equal to 0.12. The value of y we have to compute is 0.12. So how many steps we have to take if we choose our step size as 0.02? So here you will find that our x1 will be x naught plus h. So x naught is 0 plus h is 0.02. Okay, so this will be our x1, and our x2 will be x1 plus h. This will be 0.02 plus 0.02. This will be 0.04. Our x3 will be x2 plus h. The step size is h, so 0.04 plus 0.02, 0.06. x4 will be x3 plus h, 0.06 plus 0.02, 0.08. Bear with me, I have to complete this till 0.12. x5 will be x4 plus h. So again, this will be 0.8 plus 0.02. This will be 0.10. So my x6 will be x5 plus h. This will be 0.10 plus 0.02, so this will be 0.12. So I have to do the calculation till x6, because if I choose my step size h as 0.02, so to arrive at 0.12, I have to compute till x6. So here we know our x1. So once we know the step size, then we can arrive at this x1. Then we will calculate our y1. Y1 we will calculate using this Euler formula here. So y1 will be y naught, because here our n equal to 1. N is 1 for y equal to 1, right? So if n equal to 1, if you put this formula, n equal to 1, 1 minus 1 is y naught, like, right? So likewise, our h value is 0.02, then f of x naught y naught. So what is our y naught here? Y naught is 1, x naught is 0, so I have to turn back here and there. 1 plus 0.02 f x naught y naught. So f x naught y naught, the functional form here is x cubed plus y, right? So here you will see that x naught cubed plus y naught, x naught cubed plus y naught. Okay, so 1 plus 0.02, x naught is 0, y naught is 1. So what you're going to have here is 1 into 2, 0.02. So this will give you 1.02. So my y1 will be 1.02. So once I know y1, then I can arrive at my y2, n equal to 2. Y2 will be, according to this formula, n equal to 2, 2 minus 1 is 1. So I think you can understand here. Y1 plus h value is 0.02 again, f of x1, y1. So y1 is 1.02 plus 0.02, and x1 cube plus y, x1 cube plus y1. So 1.02 plus 0.02. What is x1 now? X1, we have already calculated the step size. X1 is 0.02, 0.02 cube plus y1 is 1.02. So this I have to calculate using my calculator. Yeah, let me just quickly calculate. 0.02 into 0.02 into 0.02 plus 1.02 multiplied with 0.02 plus 1.02. So here I have 1.0404 y2. Okay, so just 1 minute. I have to make more blank spaces here. Control C, Control V. I need more blank spaces. Control C, Control V. So I'm going to need more blank spaces in order to calculate everything here. Yeah, I have created sufficient number of blank spaces here. So we have arrived at y2. Y2 corresponds to our x2, which is 0.04. Now we have to arrive at y3 again using the Euler formula. In order to arrive at y3, then you put an equal to 3. Y3 will be equal to y2 plus h is 0.02 and f of x2 y2, and our y2 here is 1.0404. 1.0404 plus 0.02, and the functional form here is x cubed plus y. So x cubed plus y means x2 cubed plus y2. So this is 1.0404 plus 0.02, and our x2 is 0.04. So 0.04 cube plus 1.0404. Like this, I think you can continue. Like this, you will continue using your Euler formula. You can you can deduce the value of, I think here, what is that? X6 is 0.12. So if you continue like that, you just calculate till n equal to 6. So n equal to 6, y6, y5 plus h value is 0.02, f of x5, y5. So once you arrive at y5 value, you can use that to find the value of y, like corresponding to x equal to 0.12. So once you obtain the value of y at x equal to 0.12, then your problem is solved. Okay, so this is how we use the Euler method to compute the value of y from this differential equation. I think you can continue with that, because if I do every step, it will take almost like whatever allotted time here for this 1 hour Zoom lecture. So this is another problem which you have to solve using Euler formula. So here the step size you have to choose here is your h is 1/2 means 0.5. So h equal to 0.5 means here you have to compute over the interval 0, 2. So what we have here is our f of x, y is x minus y upon 2. And our x naught is 0, y naught is 1. And if you're going to use this h step size as 0.5, how many intervals you are going to need to arrive at 2 here? You have to arrive at 2 here. So that means your x1 will be x naught plus h, 0 plus 0.5. This is our x1. Then corresponding to this, you can find y1 value. Y1 value will be y naught plus h, f of x naught, y naught. Then you can obtain the next point, x2, which is x1 plus h. x1 is 0.5 plus 0.5. This will be 1.0. This will be your y2. You can obtain it using again the Euler formula, y1 plus h, f of x1, y1. And your x3 will be x2 plus h. So this is 1.0 plus 0.5. This will be 1.5. Your corresponding y3 will be y2 plus h, f of x2, y2. Like this, you can obtain. Then your x4, just a minute, your x4 will be x3 plus h, 1.5 plus 0.5, this will be 2. So your corresponding y will be y4, which will be y3 plus h, f of x3, y3, according to Euler formula. So since you are supposed to calculate over the interval 0 to 2, your initial value of x is x naught is 0, and with x4 is now 2. So you are calculating between x naught and x4. So between x naught and x4, between this interval, you can obtain all the values of y from this differential equation. So in Euler method, in Taylor series method, we use the Taylor series expansion, and by substituting the value of x, we can obtain the y value at any point. In this Euler approach, we use simply what we did is we simply draw, we consider the initial point x naught y naught. We simply draw a tangent at that point, and we obtain the slope of that tangent. The slope of the tangent is actually your differentiation at x naught. So differentiation at x naught, according to this differential equation, it will be f of x naught y naught. So this is the formula we arrive at. We are okay. I think I will have to mute one of you. Yeah, that is done. Now, here in this Taylor series, in this Euler method, I mix up the nomenclature here, sorry. In this Euler method, what we see is that the necessary condition, the necessary requirement is that here our del x, in order to have this slope, this is the slope, okay, this is the slope to be equal to this differentiation, what we need is, the condition we need is our del x has to be very small, okay. Del x, the increment has to be, the step size has to be very small. If you choose a larger step size, your calculation will lead to a wrong result. For example, if you choose a larger step size, something like this, if we choose one step like this, big step like this, then from this point, if you are let's say drawing a tangent, it might go like this, or it might go like this. So there is a chance that once you choose a very large step size, you will get a completely wrong result out of this Euler method. So there is this thing called modified Euler approach. Modified Euler approach is similar to our Euler approach. It is simply an iterative method to find a better solution. Okay, so the approach of this modified Euler method is something like this. So by the way, you have to please note down this differential equation. Note down this differential equation over here and solve it. Okay, of course I will upload this video. I think you can look at the video again and you can solve it. All right, so now this is the modified Euler approach. So as I said, this Euler approach requires a very small step size, and this Euler method gives a better approximation using this iterative approach. So the iterative approach we have is that once we obtain our y1, let's say we obtain our y1 using our Euler formula. What is that? Y1 will be y naught plus h f of x naught y naught, right? So this is our Euler formula. From this Euler formula, we can obtain, oops, yeah, the meeting will end in 10 minutes, but I think I will have to reschedule one more meeting in order to complete what I intend to complete tonight. So in this modified Euler approach, we have this Euler formula to obtain y1. The y1 is the value of y, at x1. The value of y at x1 is our y1. So this Euler method will give you a rough estimate of that, right? So in modified Euler approach, we are attempting to find a better approximation or a better result for this y1. So how do we do that? We use this modified Euler formula. So in this modified Euler formula, this is called y1. 1 means this is the first iteration result. So in this first iteration, we simply use y naught plus h upon 2 f of x naught y naught plus f of x1 y1. So x1 and y1 we obtain from this Euler formula. X1 is our x naught plus h. From this you can obtain our x1. From this Euler formula, we obtain the value of the first zeroth approximation, that is y1 here. So once we have x1 and y1, we can obtain f of x1 y1. And f of x naught y naught, like I said, this is the slope at the initial point. And to obtain the better approximation, the first iteration here, we will use this formula. Okay. And to obtain the second approximation, the better approximation, uh, we again use this formula. Here in the second iteration, instead of using the original y1, we will use y1 as obtained from the first iteration, and we can continue calculating the iterations like this. We can keep calculating the iterations like this, and unless and until we obtain y1 with a desired accuracy, we can repeatedly calculate the y1 value using this iterative formula. So the approach is something like this. And here let's say the question here is use modified Euler method to obtain y at 0.2. Okay, correct to 3 decimal places. So you can also calculate at 0.4, correct to 3 decimal places. So it's like this. So from this differential equation, you know that our f of xy is y minus x squared, and our x naught, initial point of value of x is 0, initial value of y is 1. So this is what we have. And from our Euler formula, we can calculate our y1. So let's say our x1. If I choose step size as 0.2, so let's say I choose the step size as 0.2, then x1 will be x naught plus h. X naught is 0 plus 0.2, so x1 will be 0.2, like this. Okay, we can calculate our y1 will be y naught plus h f of x naught y naught. So y naught is 1 plus h is 0.2, and this functional form is y minus x squared. So y naught minus x naught squared. So this is 1 plus 0.2. Y naught is 1 minus x naught is 0 square, right? So this will be 1.2. Your first zeroth approximation is 1.2. Now in order to obtain better approximation or better value of this y1, we will use our modified Euler method, Euler formula over here. So what we are going to do is y1 first iteration, this will be y naught plus h upon 2. Y naught plus h is 0.2, isn't it? H is 0.2, yeah, 0.2 upon 2. Then f of x naught y naught plus f of x1 y1. So y naught is again 1, and our formula f of xy is y minus x squared. So y naught is 1 plus 0.2 upon 2 is, this will be 0.1. Our f of xy is y minus x squared. So that is y naught minus x naught squared plus this will be y1 minus x1 squared. So 1 plus 0.1. Y naught is 1, x naught is 0. So y1 is 1.2, x1 is 0.2. 1.2 minus 0.2 square. 0.2 square. So we can just compute this using our calculator. I'll have to take out my phone calculator again. So this is 0.2 square is 0.2 square is 0.04. So 1.2 minus 0.04 is 1.16 plus this is 1 in multiplied with 0.1, 0.1. Then you add 2, 1 over here. So this gives me 1.216. So in the first iteration, I have 1.216. instead of 1.2, 1.216. All right. So let me go to the next iteration. So the next iteration is y1 second iteration. From this Euler formula, if you look at this, y1 second iteration will be like this. All right. So I think you can capture that in your memory. This will be my y0 plus h upon 2 and f of x0 y0 plus f of x1 y1 from the first iteration. We will take y1 from the first iteration. So your y0 is 1, your h is 0.2 upon 0.2 upon 2, x0 y0 is y0 minus x0 square plus y1 from the first iteration minus x1 square. So 1 plus 0.1 and y0 is 1, x0 is 0 square plus our y1 from the first iteration is 1.216, 1.216 minus x1 is, our x1 is 0.2, right? 0.2 square. So you can again compute this. It's very tedious, this iterative approaches. 1.216 minus 0.04 plus 1 multiplied with 0.1 plus 1. So what I have is 1.2176. Now compare with the previous iteration. In the previous iteration, the value is 1.216. Here in the second iteration, I have 1.21676. So you see that up to 2 decimal places, after 3 decimal places, 0.21, 0.21, up to 2 decimal places, we get the correct value. But the third decimal place here is 6, the third decimal place here is 7. So still the third decimal places up to place might not be accurate estimate here. So we have to do another iteration. So the another iteration we are going to do is y1 for the third iteration. So this will be y0 plus h upon 2 f of x0 y0 plus f of x1 y1 from the second iteration. We will take y1 value. So y0 is 1, h is 0.2 upon 2, and this is y0 minus x0 square plus, you can, I hope you remember our functional form is y minus x square.